Okay, so we have been in, and today we are finishing the topic of cryptography, okay? And you understand that the reason why we, in a maths subject, right? And in fact, if you go to university and you have the privilege / horror of studying maths at university, you'll find that cryptography and codes and ciphers comes under the School of Mathematics and Statistics, which is where I studied it, which is where 90% of what I'm teaching you today is about, okay? So, it's mathematical because we take this idea of a text, right? This is just revision. And we turn it into a ciphertext by means of, well, how do we do it? What's this thing in between here? What do we transform? Yeah. Okay, so we have this process of encryption. But it's not just encryption. There are lots of different ways to encrypt information, and they all involve, so far, mathematical algorithms, right? Some of them are very simple, like the very first one you learnt, which was the Caesar cipher. Very good. Okay, they get more sophisticated. They can involve some really crazy level maths when we had a look at the RSA crypto system. Okay, but there's a particular class of numbers that are very important to this whole process, right? And we spent last week looking at those kinds of numbers, how you know what they are and how you test for them. What are the most important numbers to encryption? Prime numbers. Very good. Okay, so these are going to use prime numbers a whole lot. Okay, prime numbers very, very important. And you saw, because of how we dug into the mathematical processes, why prime numbers are important. Okay, particularly to like the lock and key system, where you hand out locks, which are very you can lock messages up, but you can't open them back up. Prime numbers are kind of the key to making that work. Literally the key. Okay, but there's a second kind of number that's almost as important as prime numbers to this whole encryption process. And that's random numbers. Okay, now, just have a think about this for a second. Why might you think, and I don't want you to shout an answer, I want you to think about this for a second. Why might you think random numbers are actually important to encryption? Why might random numbers be useful and actually really, they're vital to the whole encryption process? What do you reckon, Vincent?
It makes it harder for them to decrypt it.
Okay. So, let's think about this. This is correct, but I want you to have a think about why. Can we all try and answer this question of, why is this true? Your answer was, random numbers make it harder to decrypt the message, right? And naturally, you want decryption to actually be hard, because if it were easy, then people could find out whatever your secrets were, okay? So, follow-up question then. This is true, but why is it true? Why would random numbers make it harder to decrypt? What do you reckon, Andy?
Because you don't know what to expect, you don't know which numbers or you don't know what numbers will come up.
Okay, so let's get at that idea, okay? That phrase you just said, you should all write down because it's very important to this whole process, that you don't know what to expect. Don't know what to expect. In other words, to put it in a single word, right? Random numbers are unpredictable, right? That's why you don't know what to expect. And unpredictability is really important to encryption, because if it's predictable, if I know exactly what you're going to do next, then I can decipher your message, right? And this idea here is the whole principle on which, after the Caesar cipher, we learned a second method of encryption. Do you remember what it was? It was what the Germans used, kind of, right? There was a piece of paper that was involved. One-time pads, right? So one-time pads are kind of the embodiment of unpredictability. There is no way you can work out what's going to come next, okay? Which is why it's unbreakable, right? So, random numbers, right? What makes a series of numbers random is two things. The first is that they're unpredictable. You don't know what to expect, okay? So this is kind of like property number one, okay? The second property is what we call uniform distribution. Okay? Which means that all of the numbers in this range, right, they're all equally likely to occur. Okay? If they're not all equally likely to occur, for instance, if it's far more likely to get, if you had a die, okay, and you were rolling it, and like half of the time you rolled sixes, 6, 6, and every second turn you got a 6, okay? There's not a uniform distribution. That's not random anymore. You would not call that a fair die anymore. You'd call it loaded or unfair, right? So that's no longer random. Something is affecting it. So these are the two qualities that we're after, right? Now, there are two ways to achieve this, okay, and we're going to draw a table to compare these two things. They're called true random number generators and pseudo random number generators, okay? So, true or pseudo, I think that's how you spell it, random number generators. Okay, so I want us to draw up a little table to compare these two things. Okay. So the first thing we're going to think about when we're comparing true random number generators and pseudo random number generators, whatever they are, okay, is how do these things work? How do they work? Okay, so a true random number generator, I gave you an example of one just a second ago. A die, right? A die or like a coin toss, those kinds of things, they're actually random. Okay, so the key here though is that I have to use something. I have to use an object of some kind. Okay, so in other words, there's a physical element to it. Okay, I need some kind of object. Now, we're not just limited to coin tosses or to rolls of the dice. You can take any kind of physical phenomenon, like listening to sounds, right? Take the sound that gets recorded off of this, and that's you can represent that digitally, and that'll give you some numerical values. But the key is it comes from a physical thing, right? And then that'll give you some sense of randomness. Pseudo-random generators, random number generators, on the other hand, are trying to think about all of these tools that we know, right? Which is that this is the domain of numbers, right? So surely there's some kind of mathematical way that we can use, like some kind of algorithm or function, and pump out random numbers in a similar way, I suppose, to how we pumped out prime numbers with our prime number generators from last week. Okay. Now, you probably can see as well, if you can take some numbers, right, and crunch through them and spit out random numbers, clearly you can do the same thing with these numbers if these are your starting points, right? So just as an example, right, you could take all of the numbers that you get from rolling the dice, and then you could, multiply them by some number. Or you can multiply them by the previous number that you just rolled, or you could add something, or whatever. You can do more mathematical transformations after you roll the dice, okay? Because suppose you want more random numbers than just 1 to 6, okay? So you can do these both together. But the idea here is that I just want to start with just numbers. No dice involved, okay? So now let's think about the properties that these two things have, okay? Will such a method of generating random numbers, will it be a uniform distribution, okay? Will there be sort of like a nice even spread? All the numbers are equally probable, okay? Well, if you're rolling dice, are all the numbers equally probable? Answer yes, right? Assuming it's a fair die, okay? If you use a mathematical number generator, can you get a uniform distribution of numbers? Now, the short answer is it depends. It depends. If you use very simple maths, it's quite hard. But if you use more advanced maths, it's actually doable. You can get a pretty even spread, and I will show you an example of this in a second. Okay. Now, what was the other thing? This, you don't know what to expect, that it's unpredictable, okay? So another way of saying this, instead of unpredictability, which is kind of an awkward word, okay, we say independence or statistical independence, right? That one number doesn't depend on the previous numbers, right? And the subsequent numbers don't depend on what you get now, okay? Now, let's have a think about this. You've got your, say, your flip of the coin, okay? So when you are flipping a coin, does one flip of the coin, okay, let's give this a go. Someone call it?
Tails.
It's heads?
Yeah.
Well done. I'm just curious, by the way, how many people said heads? Heads down. Who said tails?
Yeah, you did.
Interesting. Not 50%. Anyhow, okay, fine. Now I'm gonna flip the coin again. Okay. Someone call it.
Tails.
Heads again. Okay. Now, did the second toss of the coin have anything to do with the first toss? Answer no. They were completely independent. So hopefully I've answered the question here of, is a true random number generator which involves some kind of physical element to it, is it independent? And the answer is, yes it is. Okay. Aha. But now when you come to this idea of trying to get numbers from one to the next and using some kind of mathematical process, an algorithm, to get your generation of random numbers, right? Necessarily, all the numbers are going to be connected in some way because you're getting them through some kind of mathematical function, right? And mathematics, by definition, is full of patterns and order, right? So therefore, you're kind of busted on this one, right? And I'll show you an example of this in a second. Even quite sophisticated ways, there's going to be two problems, okay? Firstly, thinking back to your knowledge of trigonometry, okay? If you've had a look at graphs of trigonometric functions, right? Which is an example of an algorithm you can use to process numbers. We call those graphs periodic. What does periodic mean when it's talking about graphs? Yeah, look. Fantastic. So, you know, and you can see what it looks like. Here's a sine graph. And it looks the same forever. Okay. In fact, you only need to take this little section here, and you can get the rest of it. That sort of period is repeated, right? So it has a frequency. So all mathematical functions are going to do something like this, right? Another way of saying this is that these functions are all deterministic. That's a big word for you. It's also a word for philosophy. It means that if you know all the information in the situation, okay, you can exactly predict what will happen next if you know all the mathematical machinery that pumped out those numbers, okay? It's deterministic. You know exactly what's going to happen. So far, it looks like it's not a very even race, does it? Right? It looks like clearly these are a better way to go than these. Like, this is good, but this is bad, and that's a significant bad, right?
This might be a bit way out, but you know with the rolling the dice or flipping the coin, there is still a mathematical way to calculate whether it's going to be heads or tails. It might be more complex, like how hard you throw it,
okay,
or like how many times it's going to spin.
Yeah, right. So then the question becomes, okay, because you know when you think about it, I'm very glad you raised that, right? I'm going to flip this a few times, and you can see, right, that actually, you know, trying to answer this question, if you knew enough. I'm not coordinated enough to do this talk and do this at the same time. If you knew enough, then surely you actually could work out what it's going to be. It'd be incredibly complicated, but you kind of could, right? So yeah, that's the whole question of, is there something which is really truly random? As you'll see, there's kind of just random enough. Will be random for us. Okay? Anyhow, now. There is a whole reason why pseudo-random number generators, and you can see why it's pseudo, by the way. Pseudo means like, kinda, but not really. Pretty close, but it's kind of like, I can't believe it's not butter, but it's actually not butter, okay? So what's the saving grace of the pseudo-random number generator? Why do we use it? And the answer is, there's another attribute that we need to know about. And that is efficiency. Okay? So, you were watching me, right? Like, how many times, how quickly, that wasn't even a flip, how quickly can you flip a coin, right? Like, and even if you have like a whole bunch of people flipping coins or rolling dice or whatever, okay? Whatever process you use, because it has a physical element to it, which is why it's so advantageous, right? It's very inefficient. It takes a lot of time. It's very time consuming, okay? So this is a bust here. Whereas, if all you have to do is play with numbers, you give it a process, you program that, and you can get a computer to do this. And it's super efficient. You can pump out millions of random numbers here, even if they're not quite random, because of these things. But you can pump out millions in the time it takes to do a few of these. Okay, literally.